Hello and welcome back to the deep dive. Today we are unpacking a piece of research that I honestly think represents a real before and after moment in the timeline of AI.
Yeah, it really is. It's great to be here, by the way.
So glad to have you. We're looking at a paper from the Google research team, and it's titled Fine-Tuned Language Models Are Zero-Shot Learners.
Right, which sounds a bit dense, but you're not overstating its importance. I mean, this paper is essentially the bridge.
The bridge between what and what?
Between the era of, we have these massive models that can predict the next word, to the era we're in right now, where you can actually just ask an AI to do something and it just does it.
Right, the birth of FLAN.
Yeah.
Which the name sounds pretty harmless, like a dessert.
Yeah, a bit delicious, right.
Exactly. But the methodology here, which they call instruction tuning, is what effectively taught AI how to follow orders. But before we get into the how of it all, we really need to set the stakes for you listening. We need to talk about the problem these researchers were actually trying to solve.
The zero-shot struggle.
Yes, the zero-shot struggle. Can you paint a picture of the landscape just before this paper dropped?
Sure. So to understand the struggle, you have to look at models like GPT-3.
The titans.
Exactly. The titans of the industry at the time. 175 billion parameters. And GPT-3 was absolutely incredible at what we call few-shot learning.
Few-shot meaning it needed a warm-up.
Yeah, exactly, a warm-up. So if you wanted GPT-3 to translate English to French, you couldn't just tell it, translate the sentence. It wouldn't really get it.
It would just get confused.
Right. It might just repeat your sentence back to you, or it might start, writing a blog post about translation. It didn't understand the command.
Because it's just predicting the next word.
Exactly. So you had to give it 3 or 4 examples in the prompt first. Like you type, dog is Cheen, cat is chat, house is a, and then let it fill in the blank.
It was a pattern matcher. Amazing pattern matcher, but still.
Yeah.
If you came in cold, what we call zero shot, and just gave it a raw command without those examples, it just fell apart.
It really did. It didn't understand semantic intent.
So the mission of this Google research paper was to fix that fundamental disconnect, to create a model that doesn't need the warm-up examples.
Right, a model that understands the intent of a command immediately. And that is where FLAN enters the picture.
FLAN. Let's decode that. It stands for Finetuned Language Net.
That's the acronym, yeah.
And I want to get straight into the architecture here because, this isn't just a case of throwing more parameters at the problem. In fact, FLAN is technically smaller than GPT-3, right?
That's a really crucial point. It's based on Lambda APT, which is 137 billion parameter.
Compared to GPT-3's 175 billion.
Right. So this isn't one of those scale is all you need papers. This is really a data efficiency paper. They took that smaller model and fundamentally changed how it was fine-tuned.
The paper actually lays this out really clearly by comparing 3 different paradigms. And I think this is probably the best way to visualize this shift for everyone listening. So you had paradigm A.
Paradigm A was the pre-BERT era style.
Right, where you pre-train a model on the whole internet so it understands English, but it's raw.
Very raw. If you want it to do sentiment analysis, you have to fine-tune it specifically on thousands of sentiment analysis examples.
And if you want translation,
you fine-tune a completely separate version of the model on translation data.
So you end up with all these specialized savants, like one model can only do sentiment, another can only do translation.
They aren't generalists at all. You definitely can't ask the sentiment model to translate French.
Right. Which brings us to paradigm B, which is prompting.
Yeah, that's the GPT-3 approach we were just talking about. You have one giant model, you don't change its weights, you just feed it text prompts.
Which gave us generalists, finally. But they were inefficient. You had to be a prompt engineer.
And you wasted so much valuable context window space just giving it those warm-up examples.
Exactly. So then we hit paradigm C, the FLAN innovation, instruction tuning. It's like they decided to just mix the best of both worlds.
They really did. They kept the massive pre-trained model, but then they fine-tuned it on a massive mixture of tasks.
But the twist, and this is the big twist, they formatted every single one of those tasks as a natural language instruction.
That distinction is, well, it's subtle, but it is totally vital. They didn't just feed the model, input text, label positive.
They wrapped it in a conversation.
Yes.
Yeah.
They aggregated 62 different data sets, everything from reading comprehension to logic puzzles to translation.
62 is a lot of data.
It is. And for every single entry in those data sets, they created a template.
I was actually looking at the template examples in Figure 3 of the paper. They are fascinatingly human. Like, for a sentiment analysis task, they don't just ask, is this positive?
They use natural phrasing.
Yeah, templates like, write a review that is positive, or does this reviewer possess a negative opinion?
They actually created 10 unique templates for each data set.
Yeah.
10 per data set. And this was a manual process, human researchers sitting down and writing these out to ensure variety.
That's exhausting.
Probably was. But they wanted to force the model to stop memorizing patterns and start understanding semantics. Because if you always ask the question the exact same way,
The model just learns the trigger words.
right, it learns, if I see these exact words, I just output yes.
Which isn't real understanding.
Oh.
Oh, and there was one detail in the template creation that I thought was just genius. The turned around templates.
Ah, yes. The turned around templates.
It feels like a stress test for the model's logic. Can you explain how those work?
Sure. So normally in a deterministic task like sentiment analysis, the input is the movie review
Right.
and the output you want is the sentiment, right? Positive or negative.
Right.
A turned around template flips that entirely. It gives the model the sentiment, say it gives it the word negative, and asks it to generate a movie review.
Wow. So the model can't just learn a statistical correlation between the word terrible and the label negative.
Exactly. It has to actually understand what a negative review looks like well enough to generate one from scratch.
It forces a much deeper conceptual understanding.
Precisely. If you can answer a question one way, you've memorized it. But if you can answer it forwards, backwards, phrased as a statement, phrased as a question, you actually understand the concept.
And that leads us perfectly into the experiment design itself. Because if you just train a model on a bunch of tasks and then test it on those exact same tasks...
It haven't proved it's a generalist.
Right, you've just proved it has a really good memory. So how did Google prove FLAN was actually learning to follow unseen instructions?
This is where the paper gets really rigorous. They used a holdout methodology.
Okay, break that down for us.
So remember those 62 data sets? They grouped them into 12 clusters based on the type of task.
So all the translation data sets are one cluster.
Right. All the natural language inference data sets, NLI, are another cluster, sentiment is another, and so on.
And to test the model, they would hold out an entire cluster.
Entirely. So let's say they want to see if LN can do natural language inference, which is basically logic determining if statement A implies statement B. They train LLN on everything except NLI. They train it on translation, summarization, sentiment, all of it. Then, for the very first time ever, they show it an NLI task.
But it's phrased as an instruction.
Yes. They ask it, does the premise X imply the hypothesis Y?
And if the model can answer that correctly, it proves it didn't learn how to do NLI specifically.
Exactly. It proves it learned how to follow instructions in general, and it's applying that meta skill to a brand new domain.
It reminds me of the difference between memorizing a recipe and actually learning the principles of cooking.
Oh, that's a good analogy.
Right. Like if I teach you to bake a cake, roast a chicken, saute vegetables, and I explain the theory of cooking along the way, like what heat does to protein, how flavors balance.
Then you understand the fundamentals.
Yeah. I can then hand you a raw steak and just say, grill this. And even if you've never grilled a steak before, you can figure it out.
Because you've learned the meta skill. You know that grill implies heat, and steak implies a certain preparation. You aren't just blindly following a script.
So let's look at the scorecard. Did it actually work? Because building these templates, structuring the clusters, doing the holdout, it's a massive amount of effort.
It really is.
So when they finally put FLAN in the ring against GPT-3, specifically in that zero-shot arena, what actually happened?
It was a blowout. It wasn't even close.
Really?
Yeah. LN, despite being the smaller model, outperformed zero-shot GPT-3 on 20 out of 25 datasets.
20 out of 25. That is a massive margin.
And the wins weren't just on easy, low-hanging fruit. Let's look at natural language inference again. NLI is notoriously hard for GPT-3.
Why is that?
Because NLI tasks often look like weird, incomplete sentences in standard training data. GPT-3 struggles to find the pattern, but FLAN sees a natural question.
Because of the templates.
Right, and FLAN didn't just beat zero-shot GPT-3 on NLI, it actually beat few-shot GPT-3.
Wait, let me just clarify that for the listeners. LN, seeing the task for the very first time with absolutely zero examples, beat GPT-3, which was given examples to help it.
Yes.
That is wild.
It just shows the power of phrasing the task naturally. When you speak to the model like a human, it accesses its pre-trained knowledge much more effectively than when you try to use weird prompt engineering tricks.
It also crushed the closed book QA tasks, right? Things like trivia QA and natural questions.
Yeah, it dominated there. Because the instruction, answer this question, is perfectly clear. The model just digs into its pre-training data, finds the fact, and outputs it.
But we should be balanced here. It wasn't a magic bullet for literally everything, was it?
No, it definitely struggled in a few specific areas.
The paper is actually very honest about this. FLN didn't really improve performance on tasks that are essentially just pure language modeling.
Right, like common sense reasoning tasks that are phrased as sentence completions.
Like, the trophy doesn't fit in the suitcase because it is too blank.
Exactly, because the base model is already trained to predict the next word. That's its native language. Telling it, please complete this sentence, is completely redundant.
It's like telling a fish, please swim.
That's exactly it. The instruction adds no new signal for the model to latch onto. In those specific cases, FLAN was basically just tied with the base model.
So instruction tuning is only a multiplier when the task actually requires understanding a request.
Right, not just continuing a basic pattern.
Okay, now I want to pivot to what I think might be the most critical insight in this entire paper. It's kind of buried in Figure 7.
The scaling law.
The scaling laws. Because usually in AI, the general rule of thumb is that training helps everyone, right? If you have a good fine-tuning method, it should make a small model better and a large model better.
That's the assumption, yeah. But that is absolutely not what they found here.
No, it's not.
Yeah.
And it's a huge warning for anyone trying to build smaller, more efficient models. They tested this instruction tuning method on models of all sizes, right?
They did, ranging from tiny 400 million parameter models all the way up to the 137 billion parameter giant.
And what happened to the small models?
It was a disaster. Instruction tuning actually hurt the performance of models under 8 billion parameters.
It made them worse. Worse than if they hadn't been tuned at all.
Yes, negative transfer. They got worse on unseen tasks.
That seems completely counterintuitive. You're teaching them more, you're giving them all these clear instructions, but they get stupider when you test them. Why does that happen?
The researchers propose what they call a capacity hypothesis. Think of parameters as brain space, or like RAM in a computer.
Okay, RAM.
Small models just have limited brain space. When you force them to learn these 60-plus data sets via instruction tuning, they use up all their available capacity just memorizing those specific templates.
Oh, they're cramming for the exam.
Exactly. They memorize the training tasks so hard they just learn, if I see these words, output this, that they entirely lose their ability to generalize.
They don't have enough leftover neurons to abstract the actual concept of instruction following.
Right. They're just massively overfitting to the training data.
But then, once you cross that threshold, I think it was around 68 billion or maybe 100 billion parameters, something just clicks.
It's an emergent behavior. Suddenly, the model is big enough, it has enough space to store the specific tasks and learn the meta skill on top of it.
That's why FLAN works so well at 137 billion parameters.
Yes. It really suggests that this generalist ability, this zero-shot magic, is a privilege of scale. You have to be this tall to ride the instruction tuning roller coaster.
Which is honestly somewhat terrifying for the democratization of AI. It implies you need massive compute just to get these generalized reasoning capabilities.
It is a barrier, for sure. But there was a silver lining in the ablation studies, specifically regarding the number of clusters they used.
Oh, right, Figure 6. They tested what happened if they trained on fewer clusters.
Yeah, like what if we only use NLI or only use translation, and they found a direct linear relationship.
The more diverse clusters they added, the better the zero-shot performance got.
And the line didn't flatten out. It was still pointing straight up at 12 clusters.
Yeah. Which implies we haven't even hit the ceiling.
Not even close. If they had aggregated 50 clusters or 100, FLAN might have become exponentially smarter. It really validates the idea that the diversity of instructions is just as important as the sheer quantity of data.
Absolutely. Now, before we move on to the really fun stuff, we do have to address the technical skepticism, because whenever someone claims zero-shot success, the immediate rebuttal from the community is always data contamination.
Oh, always. It's the elephant in the room.
Right, because when a model is pre-trained on the entire internet, Wikipedia, Reddit, thousands of books, how do we actually know it hasn't already seen the answers to the unseen tests?
Did it actually reason out the answer to that obscure trivia question, or did it just read that specific question on a forum in 2019?
Exactly. So how did the Google team control for this? Because they seem pretty rigorous about it.
They were very rigorous. They did a very aggressive clean versus dirty data analysis.
Clean versus dirty.
Yeah, they mathematically scanned their massive pre-training dataset to look for any overlaps with their test sets. If they found a specific task example hiding in the pre-training data, they flagged it as dirty.
And did it change the results when they separated them?
Surprisingly, very, very little. They evaluated FLAN just on the clean data, the questions it definitively had never, ever seen, and compared it to the dirty data.
Yeah.
The performance drop was totally negligible. For almost all the tasks, there was no statistically significant difference in performance.
That is so reassuring. It really implies the reasoning capability is real. It's not just some parlor trick of memory.
Exactly. It validates that the instruction tuning fundamentally changed the model's behavior.
Okay, just for fun, let's look at the qualitative examples in the appendix. Because the graphs and charts are impressive, but seeing the model actually think is where it gets really cool.
The qualitative stuff is the best part.
They asked FLAN to correct a pretty mundane sentence. The sentence was, I guess I need to do laundry. But the instruction was, rewrite this in a Shakespearean style.
And FLAN's output was, to my mind, verily I suppose 'tis time I wash my clothes.
Verily, I suppose 'tis time. I love that. And that is zero shot.
Completely zero shot. It wasn't trained on some massive Shakespeare translator data set. It just somehow knows the concept of Shakespearean style from pre-training, and it applies it perfectly to the instruction.
Incredible. What was your favorite example from the appendix?
Oh, definitely the multilingual flexibility. They gave it a prompt that said, "What is Obama's profession? Answer in Chinese."
And it gave the correct Chinese characters for president, right?
It did. But think about the layers of reasoning there.
Right, because it's not just a translation.
Exactly. First, it has to retrieve the factual knowledge that Obama was a president. Then it has to translate the concept of president into Chinese. And finally, it has to follow the formatting constraint of the instruction itself.
That is complex, multi-step reasoning from just a single, simple prompt.
It really proves we've moved completely past simple pattern matching. We are dealing with semantic intent now.
We really are. Oh, and there's one final technical nugget in the paper that I think points directly to the future. Prompt tuning.
Yes, the soft prompts.
The researchers found that FLAN wasn't just better at zero shot, it was also much more amenable to prompt tuning, or soft prompts. Can you quickly explain soft prompts for the listener who might not be super deep in the machine learning weeds?
Of course. So usually we prompt models with text, right? Hard prompts, like translate this paragraph.
Right, words.
Soft prompts are different. That's where you optimize a set of numerical signals, continuous parameters, and you just stick them onto the front of the input.
Like mathematical steering wheel.
Exactly. It's a way to steer the model using pure math rather than language, and you can do it without retraining the whole giant brain of the model.
And FLAN was better at this than the base model.
Much better. It reached its peak performance much faster and with way fewer training steps than the raw LaMDA model.
Which implies what?
It implies that instruction tuning makes the model generally more cooperative. It positions these instruction-tuned models as the absolute ideal base layer for literally everything else we might want to build on top of them.
Wow. So if we zoom all the way out, what is the ultimate legacy of this paper? It really seems like FLAN proved that we don't need to be prompt engineers to use AI anymore.
That's definitely the user-facing legacy. It democratized the whole interaction.
Before this, you had to know the secret incantations to get GPT-3 to work.
Right, you had to trick it. After this, you could just talk to it like a normal person. But honestly, the research legacy is even bigger than that.
How so?
It proved that you can align a model to be genuinely helpful and general purpose simply by curating the structure of the data you feed it.
It turned the robot that just reads the internet into a helpful assistant.
Exactly. You don't need a brand new architecture. You don't need a quantum computer. You just need to talk to the model during its training phase in the exact same way you want to talk to it when you actually use it.
It really set the stage for the models we all use today. ChatGPT, Claude, Gemini.
They all absolutely stand on the shoulders of this concept, that instructions are the key to unlocking general intelligence.
It's just a fascinating look under the hood. It's not magic. It's just really, really clever data formatting. And, well, 137 billion parameters.
Don't forget the parameters. They are doing a lot of the heavy lifting.
Never forget the parameters. Now, before we sign off, I want to leave everyone listening with a thought, and it's based on those scaling laws we discussed earlier.
It's the big unanswered question.
Right, because we saw that instruction tuning actively hurt small models. but it unlocked this incredible reasoning in massive ones.
Which suggests there's a complexity threshold where rote memorization magically shifts into conceptual understanding.
And we also saw that the performance just kept going straight up as they added more task clusters. They stopped at 12 clusters, but the line was vertical.
Exactly. So the real question is, what happens if we instruction tune a massive model on 1,000 distinct clusters? Or 10,000?
Are we approaching a point where AI models stop being pattern matchers entirely and just become true generalists that can learn any new skill just by being told how to do it once?
Going from following a recipe to becoming a master chef who can just cook anything you ask for on demand.
That is the horizon we are looking at, a totally mind-bending possibility to end on. Well, that is it for this deep dive into FLAN and the origins of instruction tuning. Thank you so much for exploring this with us.
Thanks for having me. This was great.